Hello, everyone. This is for ARO 3220 feedback control systems at Cal Poly Pomona. I'm Justin Millsap along with Matthew Portugal, Andre Turpin, and William Song Kim. This is the Boeing 747 longitudinal dynamics controller. The team's objective was to design a controller for the Boeing 747 in a steady state when exposed to different external forces and moments during flight. The steady state conditions was that it wanted to be at an altitude of 38,000 feet and an airspeed of 450 knots. So then we created a Simulink model of the aircraft using its longitudinal flight dynamics. The objectives for this project was to find trim conditions necessary to maintain steady state in flight, such as angle of attack, elevator deflection, and throttle level. We then modeled the aircraft in Simulink using the linearized trimmed dynamics. And then we also wanted to perform a system stability analysis. Then we designed a PID controller in which will satisfy increasing cruising speeds to 500 knots while maintaining altitude, and also increasing cruising speeds to 475 knots at an altitude of 40,000 feet. Some limitations that we had for this was that we wanted the altitude overshoot to be less than 5%. We wanted the gain margin to be greater than 10 decibels, the phase margin greater than 45 decibels, and the ascent and descent rate less than 3,000 feet per minute. Right here is the equations that we used to find our trim conditions, and we found that we wanted an angle of attack of 5 degrees, elevator deflection at 3 degrees, and throttle level percentage of 33.6%, and these are all necessary to maintain steady state in flight. Here are our linearized dynamics. Some key things to pay attention to is the A longitude matrix as well as the B longitude matrix. Also, we have the delta X longitude and delta U longitude. The delta X longitude will be the change in theta, H, V infinity, alpha, and Q. And the delta U is the change in the thrust or the throttle level and the deflection of the elevator. And that's going to combine with the A and B matrix to create X dot, which are our trimmed linearized dynamics. Here's a Simulink model that pretty much represents the longitudinal dynamics as shown in the previous slide. You can see that the outputs are d theta dot, dh dot, d alpha dot, dq dot, and d infinity dot, which then runs through an integrator block, and it's going to feed back to the inputs of these, which is obviously the delta x. And then it runs into some summing blocks at some instances. These summing blocks pretty much add the initial trimmed values that we found before, and initial conditions that was given by Dr. Magia. What this pretty much does is it's just the error. So then these then go into the scope. The outputs of these scopes are displayed here. We can see that the altitude is consistent at 3.8 times 10 to the 4 feet, which is 38,000 feet. We have an airspeed of 450 knots. We have the elevator deflection at 3 degrees, throttle level at about 33 degrees. We have no climb rate and descent rate. Our acceleration's at 0. Elevator angular rate's at 0 because there's no change. And the main thing is also our angle of attack is at 5 degrees.
Okay, so for objective 3.1, what we did was basically work backwards to find a transfer function for the system stability analysis. So first we started with the ALON matrix that we had developed in MATLAB. We found the eigenvalue of every single value in that array. Once we had these eigenvalues as shown in the text box here, we only worried about the ones that had imaginary parts. So in this case, there were only 2 of them, which were the 3rd and 4th values of the array. So once we had these eigenvalues that had imaginary parts, we used that to work backwards and use those as poles to work back to a transfer function, which leads us to have 1 over s squared plus 0.1057 s plus 0.000218. So once we had a transfer function, it was just pretty straightforward of equating coefficients to the general equation of 1 over s squared plus 2 zeta omega n s plus omega n squared. And ultimately that gave us a zeta value of 0.0148 and omega n value of 0.3579. So that means that the system is underdamped because the zeta value is between 0 and 1, it's just slightly above 0. Now, when it came to testing different disturbances for the uncontrolled system, we use the initial conditions shown here at the bottom. So the delta Q naught was 0 degrees and the delta V infinity was -5 knots. So the values that came out in the scope for this system disturbance are shown here in the scope. And then based on these values, we went about the PID tuning and then kind of seeing how we wanted the PID controller to alter these responses given a system disturbance.
So for objective 4, the task was to create a controller that can perform changes during steady state flight. The first scenario that we had to look at was increasing the cruising speed by 50 knots to 500 knots and maintain the same altitude. And the second task was to increase the cruising speed to 475 knots and increasing the altitude to 40,000 feet. The way we did this was by implementing two PID controllers, one in charge of the airspeed, which corresponds to the throttle percentage, and another PID controller for altitude, which corresponds to the elevator deflection angle. Below, you can see the PID values that we use for these controllers, and these PID values in the controllers work for both scenarios. You can also see the gain margin and phase margin of each controller, and these both meet the requirements of the gain margin being greater than 10 decibels and the phase margin being greater than 45 decibels. On the right, you can see how we implemented these PID controllers. Another important thing that we had to implement was the step input. The final value for the step input was the delta between the requirement and the actual. So for example, if we needed to increase our altitude to 40,000 feet and we're at 38,000 feet, then the final value is going to be 2,000 feet. This is going to be the results for the first objective, so increasing our cruising speed by 50 knots to 500 knots and maintaining the same altitude. The first graph you can see on the left is the altitude graph, and it does have an overshoot of around 170 feet. But you can see right next to that is the airspeed, which increases 50 knots relatively quickly to 500 knots. A couple of things to point out is the angle of attack decreased, the pitch angle decreased, and the elevator deflection angle increased. It does meet the requirement, though, of staying within plus or minus 20 degrees. And one more thing on the right is the throttle level percentage, which does stay within the requirement of 0 to 100%. This is going to be the results for the objective 4.2, so increasing altitude by 2,000 feet to 40,000 feet and airspeed to 475 knots. And same thing, the altitude does increase to 40,000 feet relatively quickly, but it does stay within the climb rate requirement of 3,000 feet, just on the cusp. And the airspeed does increase by 25 knots to 475 knots. There are other requirements that need to be met that are met, is that the elevator deflection does stay within plus or minus 20 degrees, and the throttle level does stay within 0 to 100%.
And hello, lastly, for conclusions, we have for conclusion of objective 1, we were able to find the trim conditions as shown. We had the value of 5 degrees for angle of attack, 3 degrees for elevator deflection angle, and 33.64% for throttle level. And we use these conditions as the baseline for a steady flight. Next, for objective 2, we're able to find that the Simulink model was utilized to observe the trim condition and the response to different stimulus, demonstrating in objective 3 and 4 that it was working. For objective 3.0 and 3.2, we're able to confirm that the Simulink model was able to show the output even with different delta values for different cases and still met the wanted output. And it has a really efficient steady state. And lastly, for objectives 4.0 to 4.2, we're able to find the correct values for the PID controller of the Simulink that successfully satisfy all the requirements of the objective of like change in velocity and change in altitude. Thank you.